Okay, I'm really kind of excited for this video because we are now going to put everything that we've learned so far. We're going to put it all together and we're going to actually use it now as a tool for research. Okay, and so I will show you all the different places where we're going to sort of plug in the information that we know to answer some questions once we collect some data uh, and do research. I'm assuming, I'm going to use examples, a variety of different examples, but I'm assuming that you can sort of extrapolate from these examples to something that you might be interested in yourself, um, or that when if you go on to graduate school or if you're working in an agency and you're doing some kind of research, you'll be able to see how the procedures that we're going to develop work for your specific examples. Okay, so let me tell you about some of the research that I've done in the past. I don't do this kind of research anymore, but whatever research I do, I'm still using these same tools. That's what's really nice about this. It's generalizable to a lot of different areas. So one of the things I was interested in for several years, I was doing research in factors which influence people's taste perception. Okay, so I was interested in sensation and perception, and specifically human taste. And what I was doing was looking at sweetness. So I would give my subjects a sucrose solution, and then I would ask them to tell me, how sweet do you think it is? Now, instead of a Likert scale, that is that scale from 1 to 10 or 1 to 6 or whatever, I could have used a Likert scale and to ask something like, on a scale from 1 to 10, how sweet do you think this solution is, where 10 is really sweet, and so on and so forth. I used a different tool, and it gives me even more resolution than a Likert scale from 1 to 10, and that is, I would use something called a visual analog scale. Visual analog scale, okay? And this is a sheet of paper, and I'm going to do this landscape. And then on this sheet of paper, I'm going to make a line like this. And on this end, I'm going to say, not sweet at all. And over here, I'm going to say, very sweet. Okay. And then have people place an X along this line to tell me how sweet they think that the solution is. So they would taste the solution and then put their X here, okay? And someone else might taste that solution and they would put their X here, okay? So what that's telling me is the first person is rating it as tasting more sweet than the second person, all right? Now, remember, when we talk about operational definitions, I need to come up with a quantity for how sweet the people are indicating the solution is. So what I'm going to do is I'm just going to measure from the origin out to where they place their X, and I'm going to measure that in millimeters. And so this person may say that they're at a sweetness rating of 84, and this one may be at a sweetness rating of 118 or something like that. That is millimeters. But the larger the number, the sweeter the person is indicating the solution to be. Okay? So the larger number means it's closer to the sweet. Now, it's called a visual analog scale because before we do these measurements, there's no numbers there for the subject, like a Likert scale from 1 to 10. There's no numbers here, so they're going to do this in an analog fashion, And typically I can fit a line of about 200 millimeters in a landscape page. So that would be sort of the maximum sweetness rating. And again, the higher the number, the sweeter the solution. Okay? So the numbers I'm going to be using relate to these measurements on the visual analog scale. I just want people to be oriented to the numbers that we're going to be using. So one of the things, I had a student, his name was Stan Hewlett. He actually went on to get his physician's assistant degree, at least the last I knew. But he worked with me in my lab, and one of the questions that he was interested in is whether or not the color of the solution, of the sucrose solution, whether or not that would influence how sweet people perceive the solution to be. Okay? So does color influence sweetness perceptions? Now, I thought that was a good question, and I said, okay, well, let's do this in the lab, all right? And so what we did was for the subjects coming into the lab, we put red food coloring in the sucrose solution. Now, food coloring has no taste, okay? It's just a color. It's made that way. There's no taste. If you blindfolded someone, they wouldn't know the difference between a red red solution or a clear solution. But the question that we wanted to ask, when people see the red, are they, does that influence how sweet they rate the solution to be? Okay? And of course, when we did this research, because I'm going to talk about sort of real data here, when we did this research, the first thing we needed to do was to conduct a color blindness test for all of our subjects, because the most common form of color blindness is red-green colorblind. And so we didn't want people to be colorblind to red, because that's what we're going to put in the solution. So we want them to, see the color. If they're colorblind to red, then the experiment doesn't work for them, okay? Now, just a little piece of research advice here. Nobody told me I had to do that. I'm running the show here, but I have to think about potential problems. You think about potential problems and then you address those. The more you can think about potential problems, the better your research design is going to be. Sometimes when people take my research methods class, they wonder why I'm such a pain in the ass with trying to find a problem. Well, if I can sort of be trained to always find a problem and I fix it, then when I can't come up with another problem, I can be more confident that my research is good research, okay? So anyway, here's what we're going to do. We're going to develop a five-step hypothesis testing procedure, okay? And we're going to use this over and over again. This is the way you approach research in terms of analyzing the results statistically, okay? So step one is to state your hypothesis, okay? But we're actually going to do two hypotheses, okay? And I'll explain why we're doing that, okay? So the two hypotheses, let's call this H sub 0, and we'll call this H sub 1. Now, some books will call it H sub 1 and H sub 2. Some books will call it H sub A and H sub B. We're going to go with H sub 0 and H sub 1, okay? And I'm going to start with this one first, and and then we'll get to H sub 0, okay? So what do you think was our hypothesis for this experiment that I'm doing with my student Stan? What do you think the hypothesis was? Well, the hypothesis is that putting red food coloring in the solution, in the sucrose solution, will change the way people perceive that solution. Now, if you're paying attention carefully, I did not say that the red food coloring is going to increase the sweetness of the solution. I did not say the red food coloring was going to decrease the sweetness of the solution. My hypothesis is that the red food coloring is going to affect or have an influence on people's sweetness. Okay? So that's my hypothesis. And what I'm implying here is that compared to people drinking the sucrose solution when it's clear, if I add red food coloring, then it's going to change the way people perceive it. So this is called a non-directional hypothesis. I'm not going to make a guess about the direction. I'm just going to say, I think the red food coloring is going to affect sweetness perception. That means it could either increase or decrease. Okay? Now, when we went into this experiment, I certainly thought that if we added red food coloring, it's going to increase sweetness ratings, if it did anything. Because I'm thinking of people drinking this red sucrose solution compared to clear, okay? But I'm going to do this in symbols here, and I'm going to say, compared to what we see for clear sucrose, I think I'm going to see something different when I look at people having red food coloring, okay? If I wanted to say that the red food coloring is going to increase sweetness ratings, and then I might do something like this, okay? If I thought it was going to decrease, then I'd put the lesser than sign. But I'm not going to do that. And hopefully it'll become clear why I'm not doing that. But even a priori, that is before we did the experiment, this is the hypothesis that we're going to test. Because this subsumes the notion that red food coloring is going to increase sweetness ratings. Okay? What is this now? I mean, here's our sort of experimental hypothesis. What is this? Well, this is called the null hypothesis. Okay? This is the null hypothesis. And what we're going to do is the null represents a treatment not having an effect. So here's what the symbols would look like. That the mean for the population of people that are tasting clear sucrose is going to be the same as the mean for the population of the group that's tasting the red. In fact, it would be one and the same, okay? Down here I'm saying, compared to the population of folks that would drink a clear solution, that if, compared to that group, if they drink red food coloring, we would see a difference in the sweetness rating, okay? So this is the experimental hypothesis. We're going to call that something a little bit different later, but for right now. Now, sometimes people say, well, gee, why do I have this null hypothesis here? Why don't we just test this? Because I'm going to tell you, we're really going to test the null hypothesis, okay? There's a reason for this, and that is it's much more difficult to prove something than it is to disprove something. This is just straight up logic 101, okay? It's virtually impossible to prove something, but it's easy to disprove something. Let me give you an example, and hopefully this is kind of silly enough that you might, help you remember things. Suppose I had a hypothesis that all cows in some county, all the cows in that county have 4 legs. Okay, well, we can set out to prove that hypothesis. I go to knock on a door, ask the people, do you have any cows? They slam the door, and I knock again. I'm doing a research project. I need to know if all cows have 4 legs. Can I see your cows? You go out and see the cows. Yes, 4 legs, 4 legs, 4 legs, 4 legs. Okay. You go to the next house. Do you have any cows? How many cows would I need to see to prove the hypothesis that all cows have 4 legs? Well, of course, I would have to see every cow, right? I have to see every instance of whatever it is I'm looking to prove. I'd have to see every instance. So, and if I said, if I wanted to look at cows in a state or cows in the country or cows in the world, it's virtually impossible to prove the hypothesis because I have to see every instance. Well, how many cows would I need to disprove the hypothesis? Well, yeah, of course. If I go to neighbors and I say, can I look at your cows? And all of a sudden, there's 3-legged Betsy. Oh my goodness. Okay, the 3-legged cow. That's an utter disgrace. Utter. Okay. I'm just trying to milk it. Oh boy. Anyway, I hope that illustrates that all I need to do is see 1 cow to disprove the hypothesis that all cows have 4 legs. Okay? Just an example of the fact that it's very difficult, virtually impossible to prove something, and it's easier to disprove something. So here's what we're going to do. We're going to use this Logic 101 here. It would be difficult for me to prove this hypothesis. But what I'm going to do is I'm going to see if I can disprove this hypothesis. If I disprove this hypothesis, then all I'm left with is this one. These 2 hypotheses need to fulfill 2 requirements. That is, they need to be mutually exclusive from one another. In other words, my data can't fit in here and in here. They need to be mutually exclusive from each other. But taken together, they need to be inclusive of any possible outcome. So all outcomes would fit here or here, and these 2 are mutually exclusive. If I disprove this hypothesis, then I'm kind of, supporting this hypothesis, even though I can't prove it. Okay? And in fact, this is sometimes called the alternative hypothesis. And that is because it's an alternative to the null. But what we're going to do is we're going to focus on testing the null hypothesis, assessing whether this can be disproven, okay? And so we'll go from there. So this is step 1. We're setting up the 2 hypotheses. This one is a little bit more intuitive, right? It's kind of, this is our experimental hypothesis. I think that the red food coloring is going to be different than the clear solution, the way people rate the sweetness, okay? One of the things you have to remember is we're going to do this as a non-directional hypothesis. That is, we're not going to make a guess at what direction it's going to go in. We're just going to say red is going to be different than clear, okay? I'll pick up on that after we do this example. Even if I thought red was going to increase sweetness, which is what I thought in this experiment, I'm going to leave myself the opportunity to look at whether or not it's going to decrease. This says the same, equal. This says it's going to be different. That is the red and the clear. Okay? So that's our first step when we do our hypothesis testing. I'm going to do this. I'm going rewrite this. Okay. So step number 1. Here's my null hypothesis. Clear is going to be the same as the red. Here's my alternative. The sweetness ratings for the clear is going to be different than the sweetness ratings for the red. Okay, step 1. Step 2 now is we have to operationally define, what we mean by equal, okay? And so I want to do this graphically, and so I'm going to make my normal curve. And by the way, when we do a sampling distribution, I'm not sure if I mentioned this in the last video. If I didn't, that's my mistake. I should. When we do sampling distributions, even if you start off with a non-normal distribution, you will end up with a normal sampling distribution. So when we use samples, we really can be quite confident in assuming normality. And let's do this curve for the clear sucrose solution. Okay. And so if this is the mean for the clear group, and this is the standard deviation for the clear group, then what I'm going to say is, as long as the red food coloring group is in here, right, this should jog your memory, that's for sure. This is what's expected from the clear. But if my red group ends up being in here somewhere, if my red group ends up being there somewhere, then it looks like it's not different from the clear solution ratings. Okay? Think about this for a minute, right? If when I do the red food coloring, they look like this, well, then they don't look different from the mean. From the mean of the clear. Okay? But if our red group is out here, or our red group is here, then we can say, wow, that's very unexpected, that's atypical, that's weird, that's bizarre, that's abnormal. I don't usually see this from the clear. And so what I would then conclude is that the red looks like it's different from clear. Even though it's possible to get a clear solution out here, it's not probable. And in fact, we're going to use the standard definition of weird or improbable or unusual, and that is, as long as the red is in the middle 95%, as long as the red's in the middle 95%, we're going to say the red looks like the clear. If the red goes out into the extremes, then we're going to say that's not what I expect from the clear, so there must be something going on. Okay, try to think through this logic. It's very logical. Okay, is it possible to get something out here? Yeah, but that's like me saying that it's possible to get a fair coin and flip 99 heads and one tail. I mean, it's just not going to happen. Or that's like me saying, well, a meteor could hit my house. Well, yeah, it could, but I'm not going to run out of my house right now because I don't think it's going to happen. So middle 95%, extreme 5%, which means 2.5 here and 2.5 here, right? Middle 95 versus extreme 5, not upper 5, not lower 5, extreme 5, so it gets split up. So that corresponds to a z-score of 1.96. That corresponds to a z-score of 1.96. You can look that up in the table again, but that's the proper value, okay? I'm operationally defining this. I'm operationally defining this. This means it's unequal. This would mean that the red is equal to the clear. Okay? So, let me erase this here. I'm just sort of doing an annotated version of these steps. Step 2 is stating the decision criteria. What does that mean? Well, we're going to say, when am I going to say something's unequal? When am I going to say it's equal? If the red is in the middle, 95% equal. If it's beyond, then I'm going to say it's not equal. And we call this setting the alpha level. That's the sign for alpha, okay? And we're going to do this. We're going to say alpha is equal to 0.05. That means I'm going to say it's equal if the red is in the middle, 95%. If it goes into the extreme 5%, that's what this says, then I'm going to say I think the red group is different. And I'm going to kind of state the z-score that defines this extreme 5%. So this is called setting the alpha level. 0.05, we're going to use the z-score of 1.96. Now, somebody would ask the question, well, do we always do this? Do we always do this? And I'm like, well, this is going to be our standard. There are times when this can be changed, but for the purposes of this class, we're typically going to use this every time. We can talk about a different example, but most of the time we're just going to use this, okay? So now we need to collect some data. And that's sort of step 3 is collect your data. Your data and do your statistics. Now, I want to know what the population of people that would be tasting a red solution would look like. Now, this gets a little bit funky for some people. This is a hypothetical population, okay? This is why we're doing inferential statistics. I really have a canvas bag, like we worked with before, and the canvas bag is the population of people tasting a red sucrose solution, okay? That's the population. I want to try to make a guess about what that mean looks like, what the mu looks like, okay? And then compare it to the clear mu. So let's do this. I don't want to just ask one person to taste a red, red food coloring in a sucrose solution. I don't want to just ask one person. And remember, so this is how it all gets connected, you guys. This is how it all gets connected. If I want to know what's in that canvas bag, I'm not going to take out one block. I'll take out 4 blocks, or I'll take out 15 blocks, or I'll take out 6 blocks. We know from the central limit theorem, we know that taking out more than one gives you more confidence in knowing what's in the bag. So I'm just doing this arbitrarily. Let's say we'll do 8 people. So 8 people come into the lab. We're going to give them a color blindness test, and then we're going to have them taste a red colored sucrose solution, have them rate how sweet it is, and then we will do our statistical analysis from there, okay? So we have 8 people. Let's say for those 8 people, and I'm going to subscript this with red, okay? They're getting the red food coloring. Let's say for these 8 people, the average sweetness is 65.25 65.25 millimeters. Okay? So what we need to do is compare that sweetness rating to what we see normally with the clear. Let's suppose that we know those population parameters. Okay? So this is going to be a given for this example. So given, let's say that the mean for clear is equal to, let's say, 80. And that is 80 millimeters on that visual analog scale. That's what we normally see for clear sucrose solution, okay? And then let's say that the normal variability is something like 18 millimeters, okay? Now what I want to do is I want to ask, is 65.25 equal to 80? Now, before you say, no, it's not equal to 80. Now, wait a minute. This is not arithmetic. We already did arithmetic in high school, well, in grammar school, right? We already did arithmetic. And I'm going to go back and try to ask you to think. We need to go back and forth about, putting the concepts now together with a real practical problem here. If I flip that coin, right, instead of 50 heads and 50 tails, it came up 52 heads and 48 tails. I hope that you're not going to accuse me of having an unfair coin, because 52 heads and 48 tails, I mean, that's close enough to 50-50, right? We're going to go back to our normal curve. I'm not going to say it's an unfair coin until it gets further out. So the same thing is happening here. 65.25 compared to 80. I know that's not an arithmetic equality. That is, I know this is different than this. But I want to say, is it a lot different, a little different? Okay. And of course, that's where z-scores come in. So we talked a lot about z-scores with tests and comparing athletes and so on and so forth. Same logic. And in fact, again, this is why this course is extremely cumulative, because we can't just learn this, forget about it, because we're going to take our probability discussion with us, we're going to take central limit theorem with us, we're going to take standard deviation with us, we're going to take z-scores with us. That's how it works, okay? So I'm going to show you this graphically. So I'm going to erase this step 2. So here is the clear population, mean of 80, standard deviation of 18, okay? Here would be our z-scores, 1.96, okay? However, when you're given this information, these are x values in here. Okay? But we don't have an x value. We have a mean of 8 people. I'm purposefully going a little bit slower here. I'm hoping that you might think about what that means. I'm not going to put this number into this curve. I'm going to take this clear curve. You'll see me do this a lot. I would recommend it. We really want to know what samples of 8 clear tasters look like. These are individuals. What do samples of 8 look like? What would happen if we took this curve and took out a bunch of samples of n equal 8 from the clear? We know what that would look like given the central limit theorem And what would it look like? It would be less variable. So this is for clear, folks. This is for clear. It would have a mean of all the sample means equal to 80. Yes? Okay. It would have a standard deviation equal to the original standard deviation divided by sample size. Square root of the sample size. Okay. If I want to, I have 8 people in my red group, so I want to look at what do samples of 8 look like for clear. Now these are means. Now these are means for samples of 8. Okay, so that would be 18 divided by the square root of 8. Okay, so square root of 8, let's do this, 2.83. So 18 divided by 2.83, 6.36. Now, that's the number, right? But we knew ahead of time that when we go from individual people tasting clear to groups of 8 tasting clear, we knew that the standard deviation was going to be less. How do we know that? From the central limit theorem. Yeah, you got to bring that, we got to bring that with us. Okay. Once you convert over here, we don't need to pay attention to this anymore. And beautiful thing about this, for any distribution, doesn't matter if it's a sampling distribution or individuals or whatever the numbers are, a z-score of 1.96 defines what is weird, defines what is abnormal, defines what is unlikely, improbable, and in fact defines equality versus inequality. Anything in here, we'd say the red is equal to clear. Anything out here, we say it's unequal. Okay? So, and by the way, this corresponds to our step 2, right? All right, now we have to do the statistic. Let me erase this here. This is what clear groups look like. I want to know if the red food coloring group looks like a clear group. If they're in here, they look like a clear group. If they're out there, they don't. So here's what we're going to do. We're going to do our z-score. I'm going to compare my red group to the clear, because I want to, just because we subscript this with red, I don't want to presume that it had an effect. So I'm going to say, does this mean looks like it belongs here or not? And then I'm going to divide by the standard error. Everybody with me? So 65.25. Let's compare that to 80. Remember, subtraction is just our comparison. I'm going to compare this to 80, but I'm going to do that in terms of the standard deviation, because I don't expect every sample to be at 80. I don't expect every individual to be at 80. I don't expect every sample to be at 80. So how far is this away from 80? But then how does that compare to the standard distance away from the mean? And if I do this, 65.25 minus 80 equals, divided by 6.36 equals, minus 2.32. So this is what is called our test statistic, okay? Step 1, set up your hypotheses. Step 2, talk about your decision criteria. Alpha level of 0.05, extreme 5%, that's what that is. And that's the corresponding Z. Collect your data, do your statistics, But remember, if you have a sample of 8, you need to convert this to a sampling distribution with samples of 8. These are individuals. I'm going to compare my samples to samples. If this was an individual, I could use these parameters. This is a group of 8, so we know it's going to come in. Take your time, folks, okay? If you think it through, if you're just trying to learn rules, good luck. I mean, it's really hard doing it that way, okay? So we have a negative z-score here. So our red group is down here, by the way. So our red group is here, right? Negative 2.32. Well, that doesn't look like what clear groups do. Is it possible that a clear group would give me a mean like this? Yeah, but it is so unlikely. I mean, that's in the bottom 2.5%. So I have two possibilities. Either the red food coloring didn't make a difference and I got a really, really weird group, or the red food coloring did make a difference. It caused the sweetness to be rated lower. So we have to make step 4. Step 4 is make a decision regarding the null. Okay? We're always going to make a decision relative to the null hypothesis. So let's go back to the two hypotheses. If this is the case, then I would expect to see the red food coloring group in here, right? This is still what's expected. If this is the case, this is where I would place my bet for the red, if this is the case. But my red group is out here. Does it look like that red group belongs to this distribution? It just doesn't. If it did, it would be highly improbable. Again, talking about probabilities, not possibilities, probabilities. I just don't think that this doesn't look like most of the clear group. So what I'm going to do in this case, because my z-score out here is 2.32. 2.32. My decision about the null is going to be this. I'm going to reject the null hypothesis. The two possible decisions, the only two that I will accept on an exam or a homework, is you reject the null or you fail to reject the null. That's how you write it. You reject the null or fail to reject the null. Now, here's where people have some problems with this because it's a double negative, right? I'm rejecting the null. I don't think that there's not a difference. Everybody with me? And I'm like, you know what, you guys? You're in college. You got to be able to deal with double negatives. It's not that difficult, but you have to think. If I said to you, I'm not going to go to the grocery store tonight, what would that mean to you? Yeah, I'm going to the grocery store. Okay? It's a double negative. Take your time, think this through. The null says that there's no difference. If I reject the null, I'm saying I don't think that there's no difference. Everybody with me? When you reject the null, you're saying you think there's a difference between the groups. Okay? If the z-score that we got was in here, then my decision would be fail to reject the null. Don't accept anything. This is double negative. We need to be careful with how we state this. All right? Step 5, which I think is, in a way, step 5 is the step that people are going to see when you report your findings. This is what you're going to see in the journal article. And if you've had any experience reading journal articles, you'll recognize some of this stuff, okay? Step 5 is your conclusion. And here's what it would look like. It appears that adding red food coloring to a sucrose solution significantly, and this is stats terminology, we say this is statistically significant, significantly decreases. And boy, I might underline that or put it in italics if I'm reporting these findings, because we thought it was going to increase sweetness ratings. What we found was it decreases sweetness ratings. Now, this is not based on opinion, and this is the important part of science. It's not based on my opinion. It is my conclusion, but it's not an opinion. It's based on these data, okay? And so I'm going to put that in as parenthetical information to show the reader. Why am I making this conclusion? Well, because we got a z-score of minus 2.32. I'm going to put a semicolon. I'm going to say p less than 0.05. Put the period after the parentheses. This is one of my pet peeves with writing. Parenthetical information is typically part of a sentence, so the period goes here. Oftentimes people would have put a period here and then put this. I'm like, no, it's going to be part of the sentence, okay? So I'm going to stop this video, but we're going to pick up exactly right here and talk about a little bit more about what this means, okay?